All right, next we come to the work energy theorem. The work energy theorem is a tool that makes things a little easier sometimes. Particularly when you're trying to find out information about the motion of a particle based on the forces that are acting on it, or vice versa, trying to find out information about the forces acting on a particle based on its motion. In order to use the work energy theorem, you consider the net work that's done on the particle and you can use that to discover information about its motion, or again, vice versa. The net work done on a particle moving over an infinitely small displacement is given by this equation here, dW net, that is the incremental small change in the net work, is equal to the net force times dr, dr being the infinitesimally small change in displacement. And we know from Newton's second law, F equals ma, that the net force is equal to mass times acceleration, but mass times acceleration is, let me make this clear, acceleration is dv dt, that is the change in velocity with respect to time. And I just wanted to make sure that my r's and my v's didn't look alike there. So we can substitute m dv dt in for f net, and we get dW net, that is the incrementally small change in work done over an infinitesimally small change in displacement, is equal to m times dv dt times dr. And you can rearrange that through various steps here and end up with dW net is equal to mv times dv. Okay. And then you substitute velocity for, basically what you did here is you substituted velocity for dr dt, because dr dt is change in displacement with respect to time, and that's what velocity is. You can then give the dot product in all the three components and integrate. So net work from point A to point B would be the integral from point A to point B of mvx dvx plus mvy dvy. That is, mv dv for the x direction, mv dv for the y direction, and then the same for the z direction. And that's equivalent to 1/2 m, because you're taking the integral. So the exponent of v goes up to 2, but then you also divide by 2. And that occurs for all of the v's in the equation. And so you can factor out the 1/2, and you can factor out the masses too, because all three masses are the same, because it's the same particle we're talking about. And that's a constant number, so it's not subject to the integral anyway. So this ends up being 1/2 m times vx squared plus vy squared plus vz squared from A to B. Or in other words, 1/2 mv squared from A to B. Or in other words, just kinetic energy at A minus kinetic energy at B. And that's the net work from going from A to B. Okay, sorry about the little pause there, but I had a feeling that that was wrong, and I got those backwards. The net work from A to B is actually the kinetic energy at B minus the kinetic energy at A. I was just checking to make sure. And okay, so that's what it is. So it's just the net work is just the difference in kinetic energies. That's the important thing. Okay, so if the object slows down, its kinetic energy decreases, and the net work on it should be negative. If the object speeds up, the kinetic energy increases, and the net work should be positive. Now you have to include all of the forces acting on the object. Turns out some of those forces may not be doing work, and so those forces, once they've been considered, could be dropped, but you do have to consider all of the forces on the object. And it makes a lot of types of calculations easier. sometimes it can be used in situations where it doesn't really make the calculations any easier, but it doesn't make them any harder either. One example where it does make things generally easier is finding the final velocity of an object sliding down an inclined plane with no friction. You could use the kinematic equation where the final velocity squared is equal to the original velocity squared plus 2g times the final location minus the initial location times sine of theta. Or you could use the work energy theorem, and that's a little bit easier because there are only two forces acting on the object in this situation, and that would be gravity and the normal force. The normal force, though, doesn't do any work, so you could ignore that, and so only gravity matters. So just considering gravity, you have the net work would be equal to the work of gravity, and that's negative mg times the final position vertically minus the initial position vertically. And this, by the way, is another way of saying change in potential energy, which I'll get to a little bit at the end of the chapter. But anyway, just as a preview, potential energy is equal to mgh, that is mass times gravity times height. Well, what we've got here is change in potential energy, mass times gravity times change in height, because your position in the vertical direction is your height. So we're kind of getting into potential energy here, even though they're not telling us. Okay, this is the net work in this situation is equal to the change in potential energy. And it's also equal to the change in kinetic energy. And change in kinetic energy could be written as 1/2 m times delta v, change in velocity, squared. So we can take negative mg yf minus yo equals 1/2 m v squared f minus v squared o. And if you work this out, basically if you take the yf minus yo and substitute in sf minus so times sine theta, and then solve for vf squared, you end up with the same answer that we got from the kinematic equations. Oops, right here. And so it ends up working out the same. In this case, it didn't really make it much easier. In fact, because we had to derive these equations, it could even be considered harder. But there are other situations where it definitely would make it easier. For instance, if the surface of the ramp were curved instead of being straight. In that case of a curved surface, the normal force is not constant, and that would be big trouble for trying to use the kinematic method or the second law method. It's working, so in that case, using this work energy theorem would be quite a bit easier. In that case, it works better because it ignores the normal force, since the normal force doesn't do any work. Okay, so some steps to solving problems with the work energy theorem. As usual, you basically want to start off by drawing a free energy diagram, including each force acting on the object of interest. And then you want to determine if each force does work over the displacement of concern. And be sure to include any positive or negative signs along with the work. Then you want to find the total work done by each force and add them up and set the total work equal to the change in kinetic energy, and then solve it. If you check your answer, just make sure, and you should check your answer, make sure that if the object has no acceleration, then the work done on it should be 0. If the object speeds up, or in other words, increases its kinetic energy, then the work should be positive. And if the object slows down, or in other words, decreases its kinetic energy, then that means the work should be negative. Okay, to try the work energy theorem on a couple examples, we come first to example 7.9, the loop-the-loop question. which involves circular motion, which we've been skipping up until now. And so it gets into some formulas that we haven't seen. And so I'm going to skip 7.9 and go on to 7.10. Okay, 7.10 is about stopping force. And in this question, we have a bullet from a 22 caliber gun, and it has a mass of 40 grains, which is 2.6 grams. And the muzzle velocity is 1,100 feet per second, which has kindly been translated into 335 meters per second. And it can penetrate 8 1-inch pine boards. I have 1 inch in quotation marks because when it comes to lumber, measurements ain't what they used to be. 2x4s are not 2 inches by 4 inches anymore, and 1 inch pine boards, they're not 1 inch. They're actually 0.75 inches each. So what is the average stopping force exerted by the wood? That's the question. Okay, so the boards do work on the bullet by slowing it down. The bullet loses kinetic energy as it goes through the boards. Assuming the bullet stops after the 8th board, that means that the bullet has lost all of its kinetic energy at that point. So according to the work energy theorem, the original kinetic energy would be equal to force times distance. The force would be the average stopping force exerted by the boards, and the distance would be the distance that the bullet penetrates into the boards. Okay, so the original kinetic energy we can also get from 1/2 mv squared. That's 1/2 the mass of the bullet times the velocity squared. Remember, the mass has to be in kilograms, so the fact that they told us the mass was 2.6 grams, well, that was kind of nice, but they could have been nicer and put it in kilograms. 2.6 grams is 0.0026 kilograms, times the velocity, which is 335 meters per second squared. And when you do that, work that out, you come out with 145.9 joules. So the net work is, again, force times distance. In this case, the net work that's being done on the bullet would be negative. So it's negative force times distance. In this case, we're using the average for stopping force of the boards because the stopping force may differ a little bit as you keep going through the wood. And also distance is being represented as delta S stop. So the change in displacement while stopping, in other words. And that is equal to negative KE original. And that's because, again, the KE is negative because it's basically the bullet is losing its kinetic energy. If you can rearrange that to find average force, you end up with the original kinetic energy over the distance that it takes to stop, or delta S stop in this case. The negative signs go away because there are two of them and they end up canceling each other out. So the original kinetic energy was 145.9 joules, and the stopping distance was 8 times 0.75 inches, but that doesn't help us very much because we need that in meters. So it's 0.75 inches times 8 boards times 2.54 centimeters per inch times 1 meter for 100 centimeters gives us a distance in meters of 0.1524. So our kinetic energy, the 145.9 divided by 0.1524 meters gives us a 957.3 joules per meter, and a joule per meter is just another way of saying newtons. So 957.3 newtons is the average stopping force for these boards. Okay. So not as bad as it seemed. And that's the work energy theorem in action. The final section of the chapter is on power. And power is basically the rate of transfer of energy or the rate at which work is done. And when we say rate, we mean with respect to time. So the average power would be change in work over change in time. And the SI unit for power would be joules per second, because the SI unit for work is joules and the SI unit for time is seconds. So joules per second. That SI unit is actually given the name watts after James Watt, the Scottish engineer, who is widely credited with inventing the steam engine. So a joule per second is 1 watt. And the watt is a metric, the symbol for watt is a capital W, and that is a metric unit, so you can use metric prefixes with watts. So a kilowatt is 1,000 watts, a milliwatt is 1/1000th of a watt, and so on. There are other units for power. Probably the best known unit other than watts would be the horsepower. And 1 horsepower is equal to 746 watts. So you can actually express power as either watts or horsepower. You could, if you wanted to, express the power produced by the engine of your car in terms of watts. In fact, in Europe, that is pretty much the standard nowadays. If you pick up one of the European car magazines and look at the power rating for the engines, it's usually given in terms of kilowatts rather than, well, it's usually given as kilowatts first and maybe given as horsepower second. But yeah, they use kilowatts for that now. You could also give the power of a light bulb as horsepower. You know, you could take what is the horsepower of a 40-watt light bulb? And you could do that. It's just another way of saying the same thing. When I say 1 horsepower is 746 watts, that is the American standard, according to, it's sometimes called the SAE standard, or the Society for Automotive Engineers. In Europe, they tend to use German industry standards, or DIN horsepower, which is a little bit different, not terribly different, but a little bit. And in Asia, they tend to use Japanese industry standards, or JIS horsepower, which is a little different still, but not terribly different. But anyway, so since we're in the US, we'll use this conversion, 746 watts. This is the average power, is delta W over delta T. Instantaneous power would be what you get when you look at the increment of work done over an infinitesimally small period of time. And so you could represent that as dW over dt. If power is constant over the whole period of time, then we can say that work is just power times the time period, you know, the length of time. The time would have to be in seconds, though, remember. If the power varies during the time period, then the watts, I'll put number there. So it's number of watts is just equal to, oh, sorry, no, that is work. Sorry, not watts. Work would be power times time, right? Work is, if the power does vary during the time period, then work is equal to the integral of power times dt. And so one thing you could do is calculate the amount of power that's expended in doing exercises. And that's what example 7.11 does. It calculates the number, or the basically an 80 kilogram Army recruit does 10 pull-ups in 10 seconds. And how much is the average, or how much average power do the recruit's muscles supply in order to move his body up and down to do that? So there's some things that we have to consider in solving this problem. First of all, work is being done against gravity in order to pull himself up. The distance of the rise and fall we're going to call delta y, up and down. And the work due to gravity is going to be mg delta y. But notice what we're saying, the work due to gravity is mass times gravity times the change in height, and mgh is also potential energy. So the work done due to gravity in this case is equal to the change in potential energy that happens basically during each cycle times the number of cycles, each cycle up and down. So that's just another way of relating work to potential energy. We don't know the actual distance that he rises and falls during each pull-up, so we're going to have to estimate that. And we'll do that in a minute. The work done by his muscles for one up and down cycle, we could say is basically the work due to gravity times 2, because the work due to gravity would be on the way up or the way down, but each cycle is up and down. So that's 2 mg delta y for the work due to gravity in one cycle. For the delta y, we can assume a reasonable value of, say, 2 feet, and that's about 0.6, or that's about 61 centimeters or 0.61 meters. And in addition, in order to be accurate, we could assume that his arms constitute about 10% of his body's mass, and the arms are not being lifted. So the actual mass that's being lifted is 10% less than the 80 kilograms that were mentioned in the problem. And so the weight lifted is 80 kilograms times 0.9, because he's only lifting 90% of his body mass, times gravity, which is 9.8 meters per second squared. And that comes to 705.6 newtons. And the average power would be the 705.6 newtons times 10 cycles times 2, because it's up and down for each cycle, times the distance, which is 0.61 meters, over 10 seconds. So it's basically force times distance. The distance is the 0.61 centimeters. Everything else here is the total force that's going into it. Okay, so that's force times distance over the time, which is work over time, and that's power. And that comes out to be 861, and the units would be watts. Okay. If we wanted to know that in horsepower, you could always just take that 861 watts and divide by 746 watts, and you'd get 1.15 horsepower. So that's about what was expended during that period. Just as an aside, if you wanted to say 60-watt bulb, and you want to know how many horsepower that is, that would be 60 divided by 746, and that's 0.08. 0.0804 if you want to be more accurate about that. So if you really want to sort of mess with somebody's head, you can say, hey, this light bulb just blew out. Give me a 0.08 horsepower bulb from the closet and see what they say. But don't feel that you have to share that with me. Okay, so that's, I think, long enough for this third segment here. We'll finish up the chapter next time. There will be a lecture Monday, but it won't be very long because we're close to the end of the chapter. So we'll finish that up and look a little bit at potential energy also. So until next time.